Hello, my name is Ahmet Kürşat Şaşmaz. Today I would like to talk about an article for exposure correction, Luminance aware color transform for multiple exposure correction, and we will benchmark it with classical methods. Here is the outline. First of all, we will define the problem and explain previous works and propose solution. Then I will move on to data collection step and methodology of our experimentation. Finally, we will discuss the results. Let's start with defining the problem. For underexposed and overexposed images, it is very irritating both perceptually and functionally for image processing pipelines. Our area focuses on transforming under and overexposed images into normal exposed images. There are classical methods like histogram equalization and gamma correction. There are also deep learning based methods, but they only transform image unidirectional, like only underexposed and normal exposed or overexposed to normal exposed. The proposed solution tries to solve unidirectional transform with deep learning methods. Let's see how our custom dataset is built. A mirrorless camera, which is Canon R10 mounted Canon 50mm prime lens was used. HDR function of the camera was used so that neutral exposed, underexposed, overexposed and HDR fused images are stored as a block. Then we use HDR as ground truth. 73 different scenes with total 2092 images were captured in Metu. Then the images were converted into JPEG format and created a JSON file to feed our experimentation script. We compared three different methods. LUCT stands for our article. CLAHE is a histogram equalization method. Gamma correction is an algorithm that optimizes gamma value, which makes the average brightness of the image to 0.5, which is half of the maximum value. We used the metrics in the article. PSNR stands for peak signal noise ratio. SSIM stands for structural similarity index measure. Finally, we run the experiments. All dataset was iterated and calculated PSNR and SSIM for every different method. Then the analysis was done. Here are the results for neutral exposure. As you can see, our deep learning method was not efficient for transforming neutral exposure to ground truth, which is an HDR image. The best solution is gamma correction. Here are the results for negative exposure. As you can see, our deep learning method was not efficient for transforming negative exposure to ground truth, which is an HDR image. The best solution is gamma correction again. Here are the results for positive exposure. As you can see, this is the first time of our deep learning method suppressed other methods. The best solution is our deep learning method for this case. Here are the results for HDR images. As you can see, our deep learning method was not efficient for transforming ground truth to ground truth, which is an HDR image. The best solution is gamma correction again, because there's no need to change the gamma, so artifacts does not occur in gamma correction, so that our PSNR and SSIM values gets bigger. Here are the results excluding HDR to HDR comparison. As you can see, gamma correction method surpasses the other ones. Here are the results including all comparisons. As you can see, gamma correction method surpasses the other ones. As a result, our deep learning model has a long way to go. The proposed benchmark in the article probably is from a model trained with specific dataset. Thank you. Have a nice day.